Hello and welcome to another video lecture. As it notes on the top, if you haven't already done so, please watch the Zoom meeting from today, which is posted on Schoology. It just gives a little bit of some review stuff, but also some background and kind of just a setup so that these notes don't seem just kind of out of nowhere. But for now, let's get into it. So our objective for today is to calculate the energy of a moving electron. Go ahead and set that up as your EQ so you know what your plan is for today, by the beginning and the end, what you should know. So we have talked about electrons moving. We've even talked a little bit of like specific colors of light. We've talked about the electromagnetic spectrum, but really all of that has been pretty qualitative, thinking about the energy of red light compared to purple light, compared to microwaves or x-rays. But what we want to be able to do today is actually put numbers into that. And that's going to be where we end this unit, is just being really specific about the movement of those electrons and the energy related to it. Well, you are going to do some calculations, so go ahead and grab a calculator. Pause the video if you need to go get it from somewhere. It'd be nice to have your own physical calculator instead of just using your iPad. That way you can keep your iPad on the video and then use your calculator and go through some calculations with me. All right, go ahead and grab that. All right, so what we're going to talk about first is how do you calculate the frequency or the wavelength of a wave? And it turns out that both frequency and wavelength are related to a constant. Before I show you that equation though, I do want to just quick make a note because we haven't officially ever defined frequency in any of our lectures. So I just want to make sure that we're in agreement that frequency is how often a wave repeats per second. So think about like that pattern that goes by every second, or cycles per second, or waves per second. Think of it related to the word frequently. So how frequently is a wave moving would be related to its energy and its wavelength. And one way we can talk about that relationship is through this equation. C equals V and lambda. V is frequency, so it's measured in hertz. Hertz is something per second. So one way to write it is cycles per second or waves per second. Another way you'll sometimes see it is 1/second, meaning that on top there's no other unit, just 1/second. So then it can also be written as seconds to the -1. Those all mean the same thing. They all mean hertz. So if you see a number with any of these labels or the label hertz, you know that that's frequency. So that's the V symbol. So it's kind of like a fancy V, more than just like the alpha letter V, so it's a symbol V. And then wavelength is something that we have seen before. It's this upside down looking Y, or kind of like backwards H. It's the Greek letter lambda. And the units for wavelength need to be in centimeters because the two things that these are equal to are the constant, the speed of light in a vacuum. So 3.00 times 10 to the 10 centimeters per second. So in order to get this to equal centimeters per second, this has to be in hertz, which is per second, and this has to be in centimeters. So then let's just talk quick about relationship between these, which will also help us make a relationship to energy. So if you have frequency times wavelength equaling a constant, if these two things are both on the same side of an equation, they have to be indirectly related. So let's think about what that means. If your frequency is really, really high, meaning it's repeating itself a lot per second, so it's a really high frequency, think about what that would have to mean for wavelength. In order to repeat itself a lot, the wavelength would have to be, think about it, small. So watch my cursor here. Kind of imagine that I'm drawing a wave pattern. So if I draw a wave pattern that is repeating itself a lot every second, the wavelength has to be pretty small in order for me to move quickly. So if the frequency is high, the wavelength has to be small or short so that this stays constant. And then the opposite then, if I have a wavelength that is really spread out, so I'm drawing this like a really long or spread out wavelength, you notice that I can't repeat it as fast. So that means the frequency is a lot lower. So if the wavelength has a high number, so a really long wavelength, the frequency would have to be a lot smaller, or short frequency, small frequency, in order to keep the the speed of light constant. So that's already kind of a relationship between frequency and wavelength. Now let's see how we actually use this. So let's go ahead and try this. If you know the wavelength, you can find the frequency, and if you know the frequency, you can find the wavelength because they're both equal to the speed of light. So let's choose green light. Now, obviously, there's different shades of green, but let's kind of pick the middle. Like the middle of the green spectrum would have a wavelength. That's this symbol. So the wavelength of green light is 512 nanometers. And the question is, okay, well, what's the frequency of green light? Because I want to maybe make a connection between energy, because frequency is like, we can think of it like movement. And so the more it is moving, the more energy it has. Just the number 512 nanometers is maybe not as much of a connection of, wait, is that a really small number or not a really small number? Is that short or long? It's harder to tell. So frequency is going to help us understand what kind of an energy this might have. So this is the original equation, C equals frequency times wavelength. Let's go ahead and plug in those numbers and see what we got. So C equals V lambda, so frequency times wavelength. What is the frequency of green light? Let's make a list of what we know. We always know the speed of light. It's 3.00 times 10 to the 10 centimeters per second. Lambda was given, so your wavelength was given 512 nanometers, which means I'm solving for V, frequency. So the first thing you might want to do is some algebra. If I want to solve for V, I'm going to divide both sides by lambda. It'll cancel here, and I'll be left with V equals C over lambda. Frequency equals the speed of light divided by the wavelength. So then I can plug in what I know. Here's my speed of light constant, here's my given lambda. And so you might, an uncareful chemist might be like, oh, I'll just divide those two numbers, get my answer. But you gotta be careful. Speed of light is centimeters and wavelength is nanometers. So if you just divide these numbers out, you're not gonna be left with just hertz or 1 over second, meaning that the top of this has to cancel so that we're left with 1 over second, which is what frequency is. Well, you could look it up, or I'll give it to you, that it turns out that nanometers fit into meters, and then we know there's a relationship between meters and centimeters, so we'll set up some good old-fashioned dA, and it's going to look like this. So here's my algebra equation, V equals C over lambda. I plug in C, and then here's my dA. The given number was 512 nanometers, which means nanometers has to cancel. Nano is little, so 10 to the 9th nano fits into 1 meter. And then 1 meter is equal to 100 centimeters. So then if you follow our dA here, so meters goes away, nanometers goes away, centimeters over centimeters goes away, and you're left with seconds to the -1. Because the only thing that didn't cancel is something over seconds. Well, there isn't anything over it because centimeters canceled, so that's seconds to the -1, which is the same as 1 over second, which is the same as hertz, which is what I wanted for my label of frequency. So then now you just have to be careful with how you type this in. Go ahead and try it out. Here's what I would recommend. I would type this in like this, 3.00 E button 10 divided by parenthesis 512 divided by 1E9 times 100 parenthesis equals, go ahead and check that out, see what you get. Here's what you should end up with. So this is your math answer. So this gives us a chance to review math answers versus science answers. We can't be more specific than the measurements we used in our problem. So this is a measurement. 3.00 is 3 sig figs. And then this lambda is also 3 sig figs. So our answer can only have 3 sig figs. So 1, 2, 3 sig figs. I look at the next number for rounding, which it does. So my science answer ends up being 5.86 times 10 to the 14th. I put the label hertz because remember all the other units canceled except 1 over seconds or seconds to the -1, which is what hertz means. We check our answer with the screen, looks good. So then now this kind of gives us an answer. Oh, 10 to the 14th, that's a pretty big number. That means that that number this is moving pretty fast. So then that tells me that there's quite a bit of energy related to green light. You could also think of it in terms of the electromagnetic spectrum. Green is sort of the middle of the colors that our eyes can pick up, which tells you that it's a little bit higher energy also because we can actually see it. So that's the idea of calculating either wavelength or frequency, both compared to the speed of light. Next, we'll start to put it into energy. But before we do that, go ahead and do your Costa level question 1. Pause the video or come back to it later. All right, here we go. Let's continue on. Now let's make a connection between frequency and wavelength and energy. We have talked about the fact that electrons start at their ground state, which is the fixed energy level that they have to begin with. And they can only jump to other levels if they absorb energy and move up to excited, or emit energy and come back down. That is referred to as a quantum of energy, and it's a very specific amount. It turns out we can calculate that. Now, before we even get into it, kind of think about the fact that we're talking about the energy of one electron moving between energy levels. Think about what that really means. Atoms are so tiny that we can't even really imagine how tiny they are. So we're talking about one electron moving from energy level 2 to 3 or 3 to 5 or whatever it's doing. the actual amount of energy that is transferring in that example is so small. So when you're getting answers related to calculating the quantum of energy, you should be expecting answers that the actual number is significantly small. So let's already have that kind of in our mind moving into it. Here's the official equation. E equals hv. Now you can imagine that E probably stands for energy. V, we've seen before, that's that frequency calculation, so hertz would be the label, and then H is the new thing. H is Planck's constant, and it's named after some guy named Maxwell Planck, another old dead white guy, but the point is he did a lot of work figuring out if I want these two things to be directly related, what number would I have to plug in? And I say they're directly related because they're on opposite sides of the equal sign. So if the frequency is really, really, really high, the energy would have to be really, really, really high to keep this a balanced, equal equation. So then Maxwell Planck was able to figure out what number could I plug in here so that this times this would equal the energy. And the number is 6.626 times 10 to the negative 34 joule seconds. Okay, well, let's see if that makes sense. I'm going to plug this number into H, multiply it by some frequency, which the label is going to be hertz, which is 1 over seconds. So really I'm taking this number, which is joule times seconds, times some number, which is 1 over seconds. Seconds times 1 over seconds will cancel. You'll be left with joules, which makes sense because that is the metric unit for energy. And then if you think about it, whatever number you multiply here times your Planck's constant, which is 10 to the negative 34, you're going to end up with a significantly small number for energy, which again makes sense because we're talking about electrons jumping energy levels inside an atom. So the actual amount of energy is pretty small for one electron at a time. Let's go ahead and try this. All right, so the question I might ask you is something like, what is the energy produced by the moving electrons that are creating a radio wave for a radio station at 102.9 megahertz? So this is an actual real question. This is an actual radio station, and any radio station that you see on your radio dial, the number that you're tuning into is measured in megahertz. Well, we recognize that hertz is a unit of frequency, and then mega just means that it is bigger than a normal hertz. So megahertz are bigger. Hertz fits into megahertz, but the number would be so big that instead of just putting hertz on our radio dial, they have megahertz. So that means that you could answer this question for any radio station. So you could plug in your own radio station if you prefer, but let's go ahead and do this example together. So I'm asking you to calculate the energy. So then I know that I'm using this equation, E equals HV. I know that Planck's constant is always given to me at 6.626 times 10 to the negative 4 joules times seconds, but then I got to figure out what frequency is. But frequency has to be measured in hertz because otherwise the units won't cancel. I can't use megahertz. So I'll plug in my Planck's constant, I'll plug in my given frequency, 102.9 megahertz, and then I will say, oh, well then I can convert megahertz into hertz because there's 10 to the 6 hertz in 1 megahertz. At this point now, I can just plug this into my calculator. So I will plug it in like this, 6.626 E button negative 34 times 102.9 times 1e to the 6, and then that will give me my calculator answer or math answer. So go ahead and try that out, see if we agree with each other. Oh, actually, before I give you that answer, let's think units, right? So in this case, megahertz cancels, seconds is still there, joules is still there, but remember that megahertz is gone and I'm left with hertz, but hertz is really 1 over seconds. So really you're taking joules seconds times 1 over seconds, so then seconds will also cancel and you'll just be left with joules. Now let's check our calculator answer together. So you get something like this, 6.8 blah, 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 times 10 to the negative 26 joules. First of all, let's see if this makes sense. Were we expecting a significantly small amount of energy? Yeah, we were, right? Because this is just electrons producing waves by moving inside an atom. So we expected it to be really small, but then this is a math answer, we got to talk sig figs. This given had 4 sig figs. Planck's constant has 4 sig figs, which means our final answer with sig figs can also have 4. So 6.818, so I can keep 1, 2, 3, 4. I look at the next number for rounding, which it does not. So 6.818 times 10 to the negative 26 joules. And again, the joules came because megahertz canceled. Hz is really 1 over second. So seconds times 1 over second cancels. You're left with joules, which is the metric unit for energy, so that makes sense. All right, so now you can actually calculate energy, you can calculate frequency, you can calculate wavelength. So if I had given you a wavelength here instead of energy, you could use the previous equation, C equals V lambda, and give the wavelength to convert it into frequency, and then frequency to convert it into energy. So that might be another example of a problem you'll see when you do some of those practice problems on Schoology. For now, though, go ahead and do a Costa level 2 question. Feel free to make up another question like this, change the radio station, or you could ask the same thing. What is the energy produced by the moving electrons with a wavelength? And you could make up a wavelength here instead. Those would be great examples of level 2 questions. All right, go ahead and pause the video so you can write that or come back to it later. All right, the last piece that I want to talk about related to this quantum concept of the small amount of energy produced when electrons move, I just want to make the connection between energy and wavelength and frequency using our electromagnetic spectrum. So radio waves, remember, are our longest, so a high wavelength, our longest waves of light, which means they would have a very low frequency. They wouldn't repeat very much. So if I try to kind of pretend to draw it, so it'd be like really drawn out like this. Low energy, long or high wavelength, low frequency. And then it just goes up from that. So microwaves would be a little bit higher frequency, a little bit shorter wavelength, a little bit higher energy. UV light would be much higher than radio waves in terms of frequency, a much shorter wavelength, much higher energy, ending up all the way to cosmic waves, which would be, in terms of what we've measured, the highest frequency that we have, the lowest or the shortest wavelength, which would then be our highest energy. So if I try to draw that, it'd be like up and down, up and down, up and down, up and down really, really fast. Okay, go ahead and finish up these notes from today with a level 3 question. You will also do a summary that answers the EQ from today. All right, that is the end of day 5. It's actually the end of your content for this first unit of Chem B. So here's the things that you want to make sure that you're taking care of. Everything from day 1 through 4 should be done at this point. The things that should have been done and submitted on Schoology are the Hey Miss K assignment from day 1, the flame test lab from day 3, the electron configuration sheet from day 4. So make sure you take care of those things. You should look at some of those practice problems that are on Schoology. They go in the back section of your notebook for math problems. Make sure you show your work. And remember, if the problem has like A, B, C, D, you only have to do one of them unless you need more practice. Those things should all be taken care of before you do the Unit 7 quiz. Just a clarification on Schoology quizzes. So you, of course, will be working on this kind of on your own. You only are allowed one attempt. So I'm trusting that you are, once you start it, you are finishing it, because if you don't finish it and you click out of it, you won't be able to get back in. And then that doesn't really show me what you know. Because you are working on your own and it's a Schoology quiz, it is basically open notes, open resources. But just to clarify, the resources you're using are the resources that you have created or I have given you. Your notes, your periodic table, of course, calculator, any of those kinds of things. You are not working with other people and you're not looking up answers online. Most of the questions are level 2 kinds of questions anyway, so that I can still kind of assess what you know, not what you can look up. So just know that I'm trusting you, just so that you can show me what you understood from this unit. So before the next class period, so you could do that tomorrow. In this case, you actually have a weekend that you could finish it up. But before the next class period, you should have finished up that Unit 7 quiz, so you're ready to go on to Unit 8. One other thing you could do, just in case you're someone who's kind of like pushing yourself and you want to know as much chemistry as you can, one of the things I kind of put on the back burner because we're doing distance learning was the 3 topics of photoelectric effect, Doppler effect, and lasers. So if you're interested in those, or just because you know you want to get as much pre-AP information as you can in case you take college chemistry or AP Chem, that would be something that you could look at. So those are optional. They won't be assessed in any way. But if you're someone who's trying to soak up as much chemistry as you can, there is an optional day 5 video notes that you can look at. Still take notes like normal. but there isn't any assignment or anything that goes along with them, but it might be useful information to have for future reference. Plus, they're just kind of interesting topics. Just another reminder about office hours. Remember, every school day, not just the day you have class, but every school day from 1 to 2, all of your teachers have office hours. If you have any questions from these notes or any of the other notes, or any questions you want to ask before you take that Unit 7 quiz, just know that that is available. So from 1 to 2 every day, you can log in, send me a message. We can have a discussion about stuff just to make sure that I can clarify things for you. And that brings us to the end of day 5 and really the end of Unit 7 for Pre-AP Chem B. Thanks for logging in. We'll see you next time.